Welcome back. I'm going to finish lecturing about DART with this lecture. Just to recap what DART is, DART stands for Directed Automated Random Testing, an independent standalone unit testing tool for a C program or Java program, and it basically does concolic execution, a mix of concrete and symbolic execution. What are the steps that DART follows? DART begins by generating a random test input for the given C program. It does enough work to figure out how to generate the random test input such that it's a correct format and test input for the C program. It runs the C program on this randomly generated inputs and collects a few pieces of information. What does it collect? It collects the details about the path that this randomly generated test input takes the C program on. It collects all the constraints that were encountered along the path, puts them in a stack. Along with that, whenever a particular constraint that it is encountering along a path turns out to be non-linear because it cannot be solved by a constraint solver, DART also keeps the concrete value, substitutes the concrete value, and raises a flag which says that I am not able to symbolically execute this particular path. After it's generated successfully the path constraint for a randomly generated test vector, DART systematically explores neighboring paths that the program would have taken by taking one constraint at a time that it encountered on this random test vector, which it kept these constraints in a stack, if you remember. Takes it out of the stack, flips the constraint, which means negates the constraint, and explores a neighboring program path. Once it's explored a particular constraint fully, it goes on to the next up constraint on the program, which is below this in the stack. Again, systematically flips it, keeps doing this. When it's able to successfully terminate doing this, then DART has done what is called a reasonably thorough directed search of a program. But at some point, if it encounters an abort statement, then DART has found a bug. So it will report saying it's found that and stop. But at some point, one of the flags, which is all linear, all locations definite, turned to be set to be 0 by DART, then means DART is abnormally terminated. Another option could be there on a non-terminating program, DART could run forever. Now, we understood the algorithm for DART. I'll tell you how for a program written in a programming language like C, DART will go about interface extraction, which it needs to do because it has to figure out what is an input to a program and how to give the program its input. How does it actually do the random test driver which generates the random input, and how the directed search is implemented. So we'll take a small example. Here is a small example of a controller that controls the air conditioning. This program is written in C. So only again, as always, a program segment is given here. So is room hot is an integer variable which is initialized to 0, which means the room is not hot. Is door closed is another integer variable initialized to 0, which means that the door is open. AC0 means the AC is off. So initially the room is not hot, door is not closed or door is open, and the AC is off. AC controller takes as an argument a message which is an integer variable. So message could take values 0, 1, 2 or 3. If message is 0, then what it means is that it sets room hot to 1, which means it starts heating up the room. If message is 1, then it starts cooling the room. If message is 2, then what it does is that it closes the door and puts off the AC. If the message is 2, then it opens the door and puts off the AC. If the message is 3, then it closes the door, and if the room is still hot, it switches on the AC. And if the room is hot, the door is closed and the AC is not on, there is an error in the program because the door is closed, AC is not on, the room is very hot, which means the controller is not working. So it goes into a state for abort. So this is like an error state for the AC control. So this is a small program which tries to take a message maybe through a reader from a user who has his AC as a part of a home control system and tries to do some simple command. We'll see how DART will test such a program and successfully ensure that it reaches this abort statement here. So now DART for C, the first step as we told you, is to do interface extraction. How does it do that? Now, apart from inputs that are initialized by a program, there could be other inputs to a program. DART first works on identifying them. How does it identify? It has to identify the external interfaces through which the program obtains its inputs. And these are typically from uninitialized memory locations because these are inputs that are not initialized. For a program written in C, typical interfaces could be its external variables, its external functions, or it could be arguments of a user specified top level function, which is the function of the program to call to start its execution. It could be any of these kinds. These external interfaces are obtained by Dart by statically parsing the code of the C program. Now, after it parses the code, how does it extract the interfaces? The interface extraction happens as follows. Inputs to the C program, how are they defined? The inputs are basically variables in the C program. So all of them will have memory locations. These memory locations are dynamically initialized at runtime when the program is running through a static external interface that Dart creates. So how does Dart do that? It supports two different ways of mapping inputs to memory addresses. First way is multiple inputs can be mapped to one memory address M, and all these inputs are obtained by successively reading M during different calls successively to the top level functions. This is a standard way in which C works. Or the same input can be mapped to different addresses because the program could take different executions. For example, the same input could be provided through an address that is dynamically allocated with a command like malloc. Anything could happen. For each of these kind of external interfaces, Dart determines the type of the input that can be passed through the program via that interface so that it can generate a random number compatible with that type. For C, type could be a basic type that is supported by C. Like for example, C supports integer type, floating point type, character, enum, and so on. It could be a struct type composed of one or more fields of other types. It could be an array of another type, a pointer. It could be any of the standard types that are supported by C. Now, what happens after this is, So Dart, while it does interface extraction, it distinguishes three different kinds of functions. There are program functions, which are basically functions or procedures that are defined as a part of the program itself. There could be external functions, which are functions controlled by the environment. They are a part of the external interface of the program, but they are not a part of the core program. So we cannot presume anything about the value that they would return. They could non-deterministically return any value of the compatible type. Or in a programming language like C, you could have several library functions, which are functions not defined in the program, but they are used and controlled by the program, so they are considered a part of it. But because they are library functions, Dart doesn't have direct access to the code of these functions. So Dart still treats these functions as unknown functions, but they are deterministic. Deterministic in the sense that I know what a function does, so it treats it like a black box. So Dart really doesn't go into the function code to instrument it or analyze it. It substitutes a value of the compatible type and moves on. So for this AC controller program that I showed you in this slide, what are the inputs? Inputs is basically this message which tells you what is the status that the room should be maintained in terms of the room being hot or cold, door being open or closed, and AC being on or off. So that's what happens in the external interface here. So it says, so this is the random test driver. So it calls a function main, and it says for I is equal to 0 to up to the maximum depth, you have a local variable called temp, and you randomly initialize temp with this int and call AC controller with this temp. So what does this random init function do? That's what we will try to understand now. So the test driver is another C program which performs the random initialization. That is this function, random init. The main function of the test driver initializes all the external variables and all the arguments to the top level function by calling this function random init. That's what this main function basically calls the random init, and then calls the program's top level function. So we will see random init in the next slide. The number of times the top level function is called, that is specified by tester. Like for example, this depth, how many times to call this random initialization? You run it once, you run it twice. That's up to us. Maybe you run it once, Dart attempted and was not successful, so you might want to run it again. So this depth value is determined by the tester. That basically calls the random init functions as many times as it is needed. This driver also contains code for simulating each the external functions in such that whenever an external function is called during a program execution, random value of the function's return type is returned by the simulated function. So here is how the random code looks like. Random init takes an argument m of a particular type. We don't know what the type could be. It could be anything that is supported by C. It could be any type. So I've just mentioned it as type, left it at this. So now we will see what it is. So if type is actually a pointer to type 2, then what you do, this is basically a random number generator. So you toss a fair coin, and if it turns out to be head, then you say it's null. Otherwise, you allot a chunk of memory of the size of type, whatever that size is, and you randomly initialize that memory to be something of this type 2. I hope this is clear, right? It's just the normal random initialization procedure. But let's say if the type, so this is a type which is a pointer to another type called type 2. So you do this, randomly allot a memory of this size and initialize it with this one. But if it's a struct type, then what you do for all fields of f in that struct, you randomly initialize each value for the field of the appropriate type. If it's an array type, let's say of some other type, if it's an array of size n of some other type, then you randomly initialize the value of the array of that same type, type 3. But if it's a basic type, then you generate random bits of that same type. So this is basically tells you that random initialization function does a correct random initialization based on whether the type being a pointer, type could be a struct, type could be an array, type could be one of the basic types. Whatever it is, it correctly allots a random input of that size, that type that is compatible to the correct size. Now, after what does random init do? It takes a memory location m and a type of the value to be stored at m as arguments and initializes m randomly depending on its type. That's what is written here. Takes a memory location m along with its type. It initializes m randomly of this type. If m is a value of basic type, then the pointer to m is initialized with the auxiliary procedure random bits, which is this, generates some bits of a compatible type. If the type is a pointer, then it's randomly initialized either with a value null or with address of a newly allocated memory location. This is the one which calls itself again because it's a recursive call. And there is a fair coin toss. So the chances here are 50-50. If the type is a struct or array, every sub-element is initialized recursively the same way. That's what is written here. If the type is of struct or if the type is of array, then you call the same random init to initialize it till you get to the basic type. Now let's go back to the test driver. So for each external variable argument to top level function, Dart generates a call to the random init in the function of the main test driver before calling the top level function. That's the part that we saw till now. The C program being tested calls an external function, let's say of something like this, let's say some function, call it some name, some fun, of some return type, then the test driver generated by Dart will also include a definition for that function. So it will say this is the return type of this function called some function. Inside that, the return type, there is a variable called temp which is of type return type, and the random init function can be called to initialize temp and return it. So what it basically does is that if there is a particular function, what Dart does is basically creates a stub for that function and returns a type that is variable that is of compatible type to the actual variable that the function would return. So once this test driver has been generated, now we can combine it with the C program to form a self-executable program that is ready for instrumentation. But once it's ready for instrumentation, then I'll go back for a minute to the code that I showed you last time, which is basically this. So it sets up symbolic memory, sets up the stack, updates the symbolic memory, keeps going, updates the stack, and does all the solving the path constraint and then runs the program. Once it runs the program, it can terminate in any of these three values. It can run forever, which is bad. It can terminate saying I have found a bug, which is good because it's able to reach the error statement, or it can systematically explore all the program paths in a program, right? So that's what it does for C after random initialization. So how does it do the symbolic updation of C? For C, it so happens that there is this OCaml application called SIL. So Dart uses this for doing parsing and analyzing C code so that it can do the symbolic update of the symbolic state. The particular constraint solver that is reported in the Dart paper is this solver called IPSolve. which they use. Basically, you could use any other interpreter that you like, or any other constraint solver that you like. I will update the correct reference that contains this paper of Dart, which mainly works for C. And Dart is actually now implemented into a full-fledged tool called Qt, as I told you in the last lecture. I'll update a reference for Qt. I'll also put in a reference for a related open source tool for C called Crest. Qt is proprietary, but Crest is open source, so that you could try out symbolic execution if you want. And if you know Java, if you're interested in symbolic execution for Java, there's a tool called JQt, which runs for Java. I'll upload a document that contains the references to each of these papers in the announcement section of the course, so that you can look at it for further details. If you have any particular doubts specifically about the Crest tool, feel free to ping me, because I've used it and tried it out, and I might be able to help you with running and experimenting that tool to do symbolic execution for C programs. So I'll stop here for now. We are towards the end of the course. What I will be doing is, I had asked you all feedback for some topics that you would want me to cover. So in the next few lectures that are available, I'm going to pick a select subset of those topics, especially those that I'm familiar with, and I'll give you introductory modules on each of those. Thank you.